Okay, we're back. We're going to continue reading through the Rust programming language, and we are on to the slice type. Slices let you reference a contiguous sequence of elements in a collection. And just jumping into their documentation on what a collection is briefly, Rust's standard library includes a number of useful data structures called collections. Most other data types represent one specific value, but collections can contain multiple values. Unlike built-in array and tuple types, the data that these collections point to is stored on the heap, which means the amount of data does not need to be known at compile time and can grow or shrink as the program runs. Okay, there's more to say there, but we're jumping ahead to a further section. So that's probably enough for now on what collections are. Now, a slice is a kind of reference, so it does not itself have ownership. Here's a small programming problem. Write a function that takes a string of words separated by spaces and returns the first word that it finds in that string. If the function doesn't find a space in the string, the whole string must be one word, so the entire string should be returned. So note, for the purposes of introducing slices, we assume ASCII only in this section. A more thorough discussion of UTF-8 handling is in the storing UTF-encoded strings or text with strings, which is covered in chapter 8. So yeah, totally. If you're not familiar with this distinction between ASCII and UTF, it's basically a combination of two topics of one, how we encode characters, or really encode our characters that we want to use in text into some kind of number system that the computer can use, and that ASCII and UTF-8 are different systems. However, in the history of it and also in the implementation, UTF-8 is a generalization. Okay, so let's work through how we'd write the signature of this function without using slices to understand the problem that slices will solve. I think that's a good approach for understanding the purpose of a thing. I can't remember why there's a main.py file in here. Oh, just playing around. Oh, I was comparing some performance stuff. Forget about that. Forget about it. Okay, so let's start with what they're writing out for a first words function. So we're going to define a function using the same syntax that we always do. And here we'll put a question mark for the moment. First word, and we're going to pass in s and a reference to string. Actually, let's put this outside of the main function for just a moment. Don't know where it's eventually going to go, but we'll find out. The first word function has a parameter of type reference to string. We don't need ownership, so this is fine. In idiomatic Rust, functions do not take ownership of their arguments unless they need to, and the reason for that will become clear as we keep going. Yeah, okay. Yeah, I'll be curious to see. I mean, certainly already we're talking about passing by reference, but the fact that the reference itself isn't like an owned thing, I'm curious to see what the explanation is. But what should we return? We don't really have a way to talk about a part of a string. However, we could return the index of the end of the word indicated by a space. Let's try that as shown in listing 4-7. So in our main RS file, let's write out the rest of the function as they wrote it. So everything looks the same so far. Function, first word, pass in s, which has a type of reference to string, and we're going to return a usize type. In the implementation, we'll say let bytes be bound to the value of whatever is returned by as bytes, which is called on not on A, but on S. This is a built-in supported thing for string, reference to strings. And then we're going to do a little loop. Reference to an item. So we're going to enumerate over it. So I is going to be an index, and the reference to the item is going to be, well, a reference to an item that we've pulled off of our iterable. And we're going to say in bytes, and iter means we're going to iterate, and enumerate means we're going to also be unpacking some indices as we go along. So if the item itself is equal to, in bytes, an empty string, return I, the index. And then we will return the length of the string if nothing else is returned. All right, So, I mean, that is in some sense a natural choice because our indices I through n minus 1 for a string of length n. I suppose this is actually in bytes, so the byte position. Oh, that's probably why they didn't cover the UTF-8 thing. Things get a little bit more interesting with bytes where you can have multiple bytes assigned to a single character in UTF-8, and they've got a whole system on how bytes can be combined to get different UTF-8 combined symbols. Not going to get into that in this video, but I can kind of see the reason now why they're doing this with just ASCII. All right, but anyway, so we're going over these indices, and we're assuming this one-to-one correspondence with an ASCII, and so we'll get 0 through n minus 1, or we'll just get to the end, in which case we'll just return the length, which is going to be n, not n minus 1. Okay, so that was the first word function that returns a byte index value into the string parameter. Now, because we need to go through the string element by element and check whether a value is a space or not, we'll convert the string that we're getting into an array of bytes using the asBytes method. That's what this step is here. The let bytes be bound to the value of s dot asBytes called, and it's a statement, so we have to end with a semicolon. Next, we create an iterator over the array of bytes using the iter method. And again, although I don't think we've covered object-oriented programming in this video series yet, but Rust kind of has its own version of it. So when we call it a method, it's kind of like a method, but it's maybe not what you're expecting if you're coming from C++ or Python. Okay, so we'll discuss in iterators in more detail in chapter 13, but for now, know that an iter is a method that returns each element in a collection, and that enumerate as a keyword wraps the, not a keyword, a method, wraps the result of iter and returns each element as part of a tuple instead. So that's your pairs here. So we get a sequence of length 2, the index, and then a reference to the item. That's, although I think here we're actually doing pattern matching and we're destructuring the pattern, something like that here. Okay, so the first element of the tuple returned from enumerate is the index, yeah. And the second element is a reference to the element, yes. This is a bit more convenient than calculating the index ourselves, sure. I mean, we could be iterating over and have like a counter of how many offsets we've done from the initial memory position, but that is nice that we don't have to do that. Because the enumerate method returns a tuple, we can use patterns to destruct that tuple. That's what I was talking about here. We're doing a destructure of this ordered pair. We'll be discussing more about patterns in chapter 6. Now, in the for loop, we specify a pattern that has I for the index and the tuple, in the tuple, and the ampersand item, which is the reference to item, for the single byte in the tuple, or the reference to it. Because we get a reference to the element from .iter.enumerate, we use the ampersand in the pattern, totally. Now, inside the for loop, we search for the byte that represents the space by using the byte literal syntax. If we find a space, we return the position. Otherwise, we return the length of the string by using s.length, or the length method that strings are equipped with. Now, we have a way to find out the index of the end of the first word in the string, but there's a problem. We're returning a usize on its own, but it's only a meaningful number in the context of the reference to string. In other words, because it's a separate value from string, there's the string type, there's no guarantee that it will still be valid in the future. Consider the program in listing 4-8 that uses the first word function from listing 4-7. Okay, so here they've got an example where, let's go down to our main function here, and they're saying let mute be bound to the value of string from hello world, more or less. Do I want to be picky and exactly match there? Sure, hello. So remember, let, we're declaring a variable to assign to s, and mute means that it's mutable, meaning it can change. And we're just creating a string from the string literal, which no, those are not the same, using this from method. Okay, so let word be bound to the value of first word, and we're going to pass in a reference to s. So the word will get the value of 5. Now, why is that? We've got 0, 1, 2, 3, 4, 5. That's where 5 will come from. And we can say s.clear. Now this empties the string, making it equal to an empty string. Okay. So I think they're going to show a problem here, which is that if we're working with let's see, this is just going to be 5. However, it's not going to, the word variable is not going to update every time s updates. And so I think what they're going to show is a kind of statefulness of s, but let's find out. So word still has the value 5 here, but s no longer has any content that could meaningfully use with the value 5. So word is now totally invalid. I mean, it's a toy example. Is there never a use case to do something that is basically this? I don't know. But I get their point, and I think they're really just showing that, look, you have a mutable variable, you describe something at a certain point in the code that doesn't last forever, and so variables based on that will not automatically update. So that's some food for thought. Storing the result from calling the first word function and then changing the string contents is what the listing 4-8 was about. This program compiles without any errors and would do so if we used word after calling s.clear. Yeah, okay, so let's give it a go. Let's go cargo run. Well, there is actually an issue here, but that is an issue entirely introduced by me. Where did I go wrong here? I want clear. You need a semicolon at the end of every statement. So there's a warning here that we didn't use word, but that's not really a substantive issue for Rust. Now, because word isn't connected to the state of s at all, meaning if I update s, it's not going to automatically update word, word still contains the value 5. We could use the value 5 with the variable s to try to extract the word out, but this would be a bug because the contents of s would have changed since we saved 5 in the word. So yeah, I think if you're trying to have throughout your code a description of what the current state of a string is, you need to be mindful to get either up-to-date information or make something that is going to automatically get the right information when you call for it. So having to worry about the index in Word getting out of sync with the data S is tedious and error-prone. Managing these indices is even more brittle if we write a second word function. Its signature would have looked like this, where fun, second word, pass in reference to a string, and we return a pair of U sizes. Now we're tracking a starting and an ending index, and we have even more values that were calculated from data in a particular state, but aren't tied to that state at all, or they won't be updated when the state of that variable s updates. We have 3 unrelated variables floating around that need to be kept in sync. Luckily, Rust has a solution to this problem: string slices. All right, let's enter into the world of string slices. Don't know if we need to update the example here just yet. Let's do it. Goodbye, first word. So let s be a mutable string taken from hello world, and we'll say let hello be bound to the value of s, and here's the slice syntax. We're going to go 0.5 in square brackets, and likewise we could grab the word world, and that one is going to be from 6 up to 11. and we need semicolons for statements like this. Rather than a reference to the entire string, hello is a reference to a portion of the string. Yes, so it's going to grab from 0 to 5 as a reference, and to a portion of the string specified in the extra 0.5 bit. We create a slice using a range within square brackets by specifying a start index, end index, all within square brackets, where the starting index is the first position in the slice, and the end position is one more than the last position in the slice. Okay, internally the slice data structure stores the start position and the length of the slice, which corresponds to the ending index minus the starting number. So in the case of let world be bound to the value of a reference to s sliced from 6 to 11, world would be a sufficient would be a slice that contains a pointer to the byte at index 6 of s with a length value of 5. So here's a diagram that shows this, where here we've got the variable s that has a pointer that goes to our index, and s also contains the length, which is 11, and the capacity, which is 11. And we also have the world variable, which has a pointer that points to 6, and we have that it contains length 5. That covers hello, and that covers world. Now, a string slice referring to a part of a string, this is like it's not really a stack and heap type of thing, but it's a similar concept here of we've got these that will be on the stack references, and we will have the data on the heap. With Rust's ... range syntax, if you want to start at index 0, you can drop the value before 2 periods. In other words, these are equal. So we can look at an example here. And all they're saying is if you want to take this slice of, they contracted it down to just hello, and I say let slice be bound to the value of ampersand s, square bracket, ... 2, semicolon, versus this other let slice, which is bound to a reference to s sliced from just no 0, but just ... 2. Rust just says that this is, the Rust compiler will recognize these as the same thing, the same object, so to speak. Not the same object, but the same meaning to the syntax. They're semantically the same. Now, by the same token, if you slice, if your slice includes the last byte of the string, you can drop the trailing number. That means that these are equal. So now we're going to look at dropping information the other way. If I say instead let length be bound to the value of s.length, and I say let slice be bound to reference to s sliced from 0 ... the length of the string, and we then can write another one which will be equal, which will be not just in the value but in the semantics of what it means, that we can also just go 3 ... as well. That just means go to the end. You can also drop both values to take a slice of the entire string. So also these are equal. Let's take a look. We have the length, and we can say let slice be bound to the value of s 0 ... length, or we can have let slice be bound to the value of reference to s sliced ... and this is really the same. ... means select everything, but then again, so does 0 ... length, where it's the length of the string. So those are basically the same. I'm not sure off the top of my head when you would really prefer one or the other, but that's good to know. Note that a string slice range indices must occur at valid UTF character boundaries. So we're not going to go into UTF-8 for this particular part of the documentation, but nonetheless, this is a bit of foreshadowing if you want to deal with some UTF-8, that you can have multiple bytes corresponding to a UTF-8 character, and that not all choices of indices are correct slices for preserving the structure of the UTF-8 characters. So if you attempt to create a string slice in the middle of a multi-byte character, your program will exit with an error. Totally. With all this information in mind, let's rewrite the first word function to return a slice. The type that signifies string slice is written as reference to stir. So in some languages like Python, like stir just is the string type and that's all that there is, but in Rust is kind of a bit more complicated in this respect of having multiple types that are all about different aspects of strings or string-like things. So here we've got fun first words. We'll pass in a reference to string and it'll return not a reference to string and not a usize as it was last time, but rather one of these references to stir. Okay, so as before, we'll have let bytes be bound to the value of calling as bytes on our input reference to string. And we'll go back to that loop for I being destructured, for I reference to item in bytes, dot iter, dot enumerate. If item is equal to the bytes value of an empty string, return reference to s sliced 0, 0 up to I, not 1. And then likewise, at the end, we can return this reference to s sliced across the whole string. So just a reference. Okay. Nice. We get the index for the end of the word the same way we did as in listing 4-7 by looking for the first occurrence of a space. That's what we did right here. When we find a space, we return a string slice using the start of the string and the index of the space as the starting and ending indices. Yep. We did that right there. We returned reference to s, sliced basically all the way up to I. Now, when we call first word, we get back a single value that is tied to the underlying data. That is, if I actually use the function here, calling first words, and we pass in s, returning a slice would also work for a second word function. I think we jumped ahead there. Strings. Now we can call the first word and get back a single. Yep. The value is made up of a reference to the starting point of the slice. Yep. Okay. Now we have a straightforward application programming interface that's much harder to mess up because the compiler will ensure that the references into the string remain valid. That's a huge deal for dealing with complexity. Mutable state is one of the things that is both necessary but can be a source of headaches when writing more complicated code. So it's nice to have some automated safeguards to catch that. Remember the bug in the program in listing 4-8 when we got the index to the end of the first word but then cleared the string so our index was invalid? That code was logically incorrect but didn't show any immediate errors. For the purpose we were trying to show, yes. The problems would show up later if we kept trying to use the first word index with an emptied string. Totally. The slices make this bug impossible and let us know much sooner that we have a problem with our code. The good old fail fast strategy. Using the slice version of first word will throw a compile time error. Okay, so we've got let mute s. We'll just tack on a little hello world into that variable, and we'll say let word be bound to the value of our first words, and we'll pass in a reference to string, and we'll try the s dot clear, and that should result in an error, a panic, and then we can go print line macro. The first word is word. And if we try to compile, we should get an error. So let's go cargo build, and we get an error. So what is the error? it got hung up on a completely unrelated thing, the usual problem. Oh, it's clear that needed a semicolon. I was right in my head of going, I missed a semicolon, but then I thought for some reason it was on the print line macro. Okay, no problem. Let's compile, cargo, build. Okay, now let's look at the problem. So we cannot find function first words in this scope. Again, I have messed up the basic parts, which we can pretty easily fix, but let's do it. There we go. This is the error we want to have. So cannot borrow s as mutable because it is also borrowed as immutable. So let word be bound to the value of first word reference to string. Immutable borrow occurs here. And then later we have s.clear, which results in a mutable borrow. And then later we've got print line macro. The first word is word, immutable borrow used later. There's our error. So recall from the borrowing rules that if we have an immutable reference to something, we cannot also take a mutable reference. Yeah, we can have one mutable reference or, and this is an exclusive or, any number of immutable references that we like, but you can't mix. Because clear needs to truncate the string, it needs to get a mutable reference. Yeah, because it needs to change it, needs to mutate it, and hence mutable. The printline macro, after the call to clear, uses the reference in word, so the immutable reference must still be active at that point. Rust disallows the mutable reference in clear and the immutable reference in word from existing at the same time, and compilation fails. Not only has Rust made our API easier to use, but it also has eliminated an entire class of errors at compile time. Better to catch it at compile time than at runtime, usually. So string literals as slices. Recall that we talked about string literals being stored inside the binary. That is, when you compile, it becomes part of the binary that is in the output. So just keep that in mind of don't throw giant amounts of strings inside of your program unless you actually need it to be there. Now we know about slices. We can properly understand string literals. So here we've got let s be bound to the value of the string literal hello world. The type of s here is reference to stir. It's a slice pointing to that specific point of the binary. This is also why string literals are immutable, whereas reference to stir is an immutable reference. That's important for being able to work on these complicated data structures. Okay, so string slice as parameters. Knowing that you can take slices of literals and string values leads us to one more important improvement on first word, and that's its signature. So in its signature, we had fun first words pass an s that has type reference to string and returns reference to stir. A more experienced Rustacean would write the signature shown in Lesting 4-9 instead, because it allows us to use the same function on both reference to string values and reference to stir. I suppose that depends mostly on what kind of constraints do you want to have, and I just think that typically this is not a constraint that we care about, and so it's often preferred to just let the more flexible case be the one that is there, but I think that also just depends. So if we have a string slice, we can pass that directly. If we have a string, we can pass a slice of the string or a reference to the string. This flexibility takes advantage of deref coercions, a feature we will cover in using deref coercions in functions and methods, which will be in a section of chapter 15. Defining a function to take a slice instead of a reference to a string makes our application programming interface more general and useful without losing any functionality. So let's try out some examples here. We've got our mute s, let's call it my string. It's still hello world basically, yes. So let's put in some examples here. Let word be bound to the value of first word reference my string, and we'll pass in a slice of my string, a reference to a slice. So what do we got here? So first word works on slices of strings whether partial or whole. Okay, so that's one example. Okay, let's look at another example. Let word be bound to the value of first word. And here we'll pass in reference my string, dot dot, which is just the whole string. Little typo there. Now let's look at another example where we have let word be bound to the value of first word, pass in reference to my string. So here, first word also works on references to strings, which are equivalent to whole slices of strings. Nice. Okay. Another example, my string literal. Hello world, sure. And we'll do some examples with that. So, first word works on slices of string literals, whether partial or whole. Now, we might sound like we're repeating ourselves here, but remember that this is actually a slightly different phrasing where up here we were talking about the string type, and down here we're talking about string literals. So let's look at some examples. Let word be bound to the value of first word called on my string literal, and we will slice my string literal from 0 to 6. Let's consider another example. Let word be bound to whatever is returned by first word called on my string literal, and slice the whole string. Now, another note. Because string literals are string slices already, this works too, which we'll look at what that is, without the slice syntax. Let's take a look. Let word be bound to the value of first word and pass in. Notice that we didn't put the ampersand here for a reference. We just passed in the name itself, my string literal. And that's because there's an idempotency here of the, like, is this already a string slice or not? It is already, so we don't have to worry about that. Even though we didn't actually say slice up here, it already is a slice as far as Rust is concerned. So that's important to keep in mind. Now, other slices. So we talked about string slices. String slices, as you might imagine, are specific to strings. It's nice when the names of things line up, although in English I tell you that sometimes you get these little annoying surprises, these little bits of nonsense that just pop up. But yes, that's great. But there's a more general slice type too. Consider this array. So let A be bound to the value of, let A be bound to this array. 5, sure. Just as we might want to refer to a part of a string, we might want to refer to part of an array. And we do it like this. We might say, let slice be bound to the value of reference A 1.3. And we could assert equality that the slice is equal to 2, 3. Since the slice has a type of reference to I32, it works the same way as the string slices do, by storing a reference to the first element and a length. You'll use this kind of slice for all sorts of other collections. We'll discuss these collections in detail when we talk through about vectors in Chapter 8. No output. Okay. So let's get on to the summary here. The concepts of ownership, borrowing, and slice ensure memory safety in Rust programs at compile time, at least these kinds of memory safety considerations. The Rust language gives you control over your memory usage in the same way as other systems programming languages. Yeah, more or less. But having the owner of the data automatically clean up that data when the owner goes out of scope means you don't have to write and debug extra code to get this control. Now, I think that that's following with resource acquisition as initialization, but doing it more automatically for you instead of like with C++, you have to kind of do it as a pattern, I think. And I think you can do this in C as well, yes. Yeah, you can do Ray, but anyways, Rust does it for you. Okay. Ownership affects how lots of other parts of Rust work, so we'll talk about these concepts further throughout the rest of the book. Let's move on to Chapter 5 and look at grouping pieces of data together in a struct. I love structs because they are just the miscellaneous collections of data that you need for organizing some of your data in memory inside of a module for how you've defined it. We'll take a look at that in the next video, and for now, hopefully that was interesting and useful to you, and have a great day.